Good morning everyone. Today we are going to discuss a next generation of cement, that is calcium sulfoaluminate cement base binder. We will look into its properties and application. As we all know that concrete is the most used man-made material in the world, so it is obvious that we need to look into the carbon footprint of Portland cement, which is the binding phase of concrete. And we know that 5 to 7% of global CO2 emission is attributed to Portland cement manufacturing. Primarily it is due to the calcination of limestone, which is used to manufacture Portland cement. So, how can we reduce carbon dioxide footprint of Portland cement? And we know that most of it is arising from the calcination of limestone. There are conventional ways of reducing CO2 emission, like increasing energy efficiency by optimizing processes. We can also increase the cementitious additions into cement. We have been doing that for a while, like adding slag, fly ash, limestone. Also we can think about substituting fuels. We can think about more environmentally friendly fuels. But we need to think of non-conventional ways if we really want to significantly reduce the CO2 emissions during the Portland cement manufacturing. So, here is the graph which compares the CO2 emission of individual phases present in Portland cement and compares it with. So, let us look into the CO2 emission of various phases present in Portland cement. C3S has the highest CO2 emission, followed by C2S, C3A and C4AF. Okay. Now, if we compare it with calcium aluminate, right, which is the main phase of calcium aluminate cement, the carbon dioxide footprint is quite low. And C4A3S, which is calcium sulfoaluminate phase, the main phase of CSA-based cements, is the least among all these phases. We know that very high kiln temperature is used to manufacture Portland cement. Roughly around 1450 degrees C temperature is used. But to make calcium sulfoaluminate cement, we need to go only to 1250 degrees Celsius. So, we can cut down the kiln temperature by 200 degrees Celsius. In addition to that, we need less grinding energy, because the calcium sulfoaluminate cement clinker is more porous. So, all these advantages lead to reduction in CO2 emission and energy requirement. So, what is calcium sulfoaluminate-Belite cement? It comprises of yeelimite, also called C4A3S, calcium sulfoaluminate, belite, as you know, also present in Portland cement, but it has a lot of calcium sulfate and calcium aluminoferrite, C4AF. So, this phase C4A3S is the main phase of CSA cement. It was patented by Alexander Klein in 1960s at the University of California, Berkeley, but the goal was to achieve shrinkage compensation in concrete, right. At that time the focus was shrinkage compensation by inducing expansion in concrete. We will look into that in later slides. Also, important thing to note is you do not need different kinds of raw materials. It is the same what you use to make Portland cement. So, limestone, clay, bauxite and gypsum is used to make this calcium sulfoaluminate cement, but the kiln temperature has to be around 1250 degrees Celsius. So, if you look into the cement, the CSA clinker has roughly 75 to 90% in clinker, rest is calcium sulfate. It is important to look into what exists. So, these are the existing CSA based products. In USA, I think there are 3 companies now which make this CSA cement, Buzi CSA cement, Component by CTS company, and this Royal White Cement company makes CSA cement. Obviously, the application is different. Sometimes they sell it as a rapid set cement, sometimes they sell it as zero shrinkage cement, that depends. In Europe, we see that this Primex, this a company based in Latvia, does not sell cement per se, but it sells concrete products. They sell it zero shrinkage concrete products. And in China, this company has been manufacturing it for decades actually. So, Overworld Trade Company Limited. So, these are the existing products in the market. Okay. It is good to know that there is something which exists, which is based on CSA cement. Now, we will look into hydration of calcium sulfoaluminate base cement. So, we know that yeelimite. So, I will use yeelimite and calcium sulfoaluminate interchangeably. So, yeelimite, which is C4A3S, can hydrate just in presence of water and gives monosulfate. You have monosulfate and aluminum hydroxide, also called gypsite. Now, when there is a presence of gypsum, you have a formation of ettringite, okay? And again you will have aluminum hydroxide. Now, when there is enough lime in the system, which may be the case when you have C2S, enough of C2S in CSA cement, or it is used with Portland cement, which we will see later in a few slides, you have only ettringite forming. So, no aluminum hydroxide. Okay. Now, as you all know that C2S can react with water and form CSH, right, calcium silicate hydrate, and this C2S can also react with this aluminum hydroxide, which is coming from these two reactions and form Ettringite. So, these are the possible reactions which may take place depending on obviously the composition of CSA cement. Although C4AF is in minor amount, but it can also hydrate in presence of gypsum and form ettringite. So, these reactions are important to always look into, and we know that whenever we have formation of ettringite, the reaction can be expensive. Okay. We will come down to this point later. How can we leverage this expansion in making concrete durable? So, here is the study done by Zhang and Glasser in early 2000, shows like if you look into the hydration products, y axis we have hydration products, and what happens when you increase the amount of gypsum, right. We know that when there is no gypsum, you will have formation of monosulfate, but as you increase the amount of gypsum, you form AFT phase or ettringite. That is what it is showing basically. So, with the increase in gypsum, you see this AFT phase is increasing, but beyond a point, like here in this case we see this 30% limit, you will have excess gypsum. Okay. Also we see formation of aluminum hydroxide. So, this study was done on this particular type of cement. Here is the phase composition. You have 48% of yeelimite, 27% of C2S, very small amount of anhydrite, right. Also, I would like to point out that it depends what is the form of your calcium sulfate, could be in form of anhydrite, could be in form of gypsum dihydrate, could be in form of hemihydrate, basanite. So, the dissolution kinetics of these individual phases will also influence the hydration of yeelimite. Again, if you look into now phase content, right. So, you start with yeelimite, right, particular yeelimite. It suppose this clinker had anhydrite, some belite. So, with the as the reaction proceeds, you see reaction of yeelimite, right. And what is important to note is just in like 4 days, 100 hours, right, roughly most of yeelimite is reacted. So, tells us that the reaction is fast, and we can expect the reaction to complete in 7 to 10 days completely. And as the yeelimite is decreasing in amount, we see increase in the amount of ettringite. Again, that will depend on the amount of anhydrite or gypsum, and depending on the C2S content, we can also see presence of Ettringite, as we have seen earlier in one of the slides. C2S can react with aluminum hydroxide and form Ettringite. So, here basically the data points, discrete data points are the measurements, and the solid lines, solid and dashed lines, the simulated plot using thermodynamic modeling. So, now we know that gypsum plays a big role. Depending on the amount of gypsum, we can either form monosulfate or ettringite or both of those, right. So, Chinese researchers have developed this formula. Basically what it says is like, based on this M is the molar ratio of gypsum to yeelimite, we can develop different types of cements: rapid hardening cement, high strength cement, expansive cement, self stretching cement, right. So, basically if M is from 1.5 to 2.5, the cement will be expansive. That means there will be increase in volume, okay. And self stressing system, you have significant expansion that leads to significant compression. We will come back to it, but important point to note is this M plays a big role in governing the volume change, okay. So, this is conventional way of looking into the shrinkage cracking of Portland cement concrete, right. What happens? You have a fresh concrete, dries, and due to restraint there is a tensile stresses developed. When the stress exceeds strength, you have a cracking. Now, in CSA concrete, if you want to leverage the expansion, right, suppose you are trying to formulate a mix which expands, what happens? This expansion will lead to some compression, right, and that compression can then counteract the tensile stresses developed due to shrinkage. So, here what I mean, in self stressing system in earlier slides, you have a residual compression, or the level of compression will be higher than just expansive system. So, now if we look into this typical shrinkage versus time plot, in Portland cement we see some level of shrinkage, right, could be 500 to 600 micron microstrain depending on the drying condition. But in the expansive system based on CSA, because of this expansion at early age, basically we are reducing the net shrinkage, right. So, there is a reduction in net shrinkage when you use CSA cement as an expansive agent. So, the point is, we know that there are advantages in terms of reducing the CO2 footprint, right. Less limestone is needed to make this cement. Kiln temperature is 200 degrees C lower than what you use for Portland cement. Grinding energy is low. Also, by leveraging this early age expansion, we can make this cement shrinkage resistant, right. So, it can be used to address both issues, sustainability and durability. Now, we will go over early age and hydration properties, hardened properties of CSA-based binder. We will look into fresh properties, right. How does it compare with conventional concrete based on Portland cement? We will look into mechanical properties. Also, we will look into early age volume change. We will also look into how do we model this early age volume change. Okay. Eventually, we will see one application. So, here is like if you make a concrete using CSA cement, because of the formation of ettringite crystals, there is a loss in slump. And if you compare with OPC, right, when you have a CSA in the system, there is a significant loss in slump. And obviously, in this study, no admixture was used initially, but we see that when you use the retarder, right, the CSA with the retarder, you can reduce this slump loss, right. And this is the conventional retarder which people use for Portland cement. And also, I would like to point out this study was done in which only 15% of OPC was replaced. So, it was a OPC-CSA blend, and the CSA cement which was used in this study had this phase composition, 20% yeelimite, 35% C2S belite, right, and the calcium sulfate in all forms was around 40%. So, we see that there is a loss in workability, but can be reduced. Now, if you want to examine, we can use isothermal calorimetry to look into this closely. So, here is the rate of heat evolution in 3 different binders. 0% CSA corresponds to plain OPC, right. Now, what happens when you add CSA, 15% CSA, 30% CSA. Now, if you zoom out this region, what happens in early few hours, we see that in OPC we see a dormant period, right, which is very useful when you have to transport the concrete, it buys some time. But in the cement where you have CSA, you have a shorter dormant period, right. Again, in the study no chemical admixture was used, and as you increase the amount of CSA, we can see they are further reducing the dormant period. This study published in 2007 addressed this, addressed the issue of this shorter dormant period by adding citric acid, right. Citric acid, basically what you can see that it is a good retarder for CSA cement. As you increase the amount of citric acid in this system CSA, you are delaying the peak, right. Again, so this isothermal calorimetry is a good tool to look into this early age hydration kinetics, right. Now, we know that okay, in the system with 3% retarder, we have delayed the hydration by 4 to 6 hours. Okay. So, this is only one example, there are other examples also. So, there are ways you can retard the CSA, the hydration of CSA cement. Now, since gypsum is integral part of this the cement, what happens sometimes, it is important to calculate the optimal gypsum. We all know that optimal gypsum for Portland cement, so roughly around 3 to 5%, right. So, again isothermal calorimetry can be used to determine this optimal gypsum. So, you see first this peak, it's because of gypsum depletion. When the gypsum is depleted, this C4A3S or yeelimite hydrates very fast, right, and releases lot of heat. Same phenomenon happens in Portland cement. When you are run out of gypsum, your C3A can hydrate, right, very fast, and their reaction is very, so you want to control that. So, you see that as we increase the amount of gypsum, right, we are basically delaying this peak, and basically the optimal gypsum is a content where beyond which the isothermal calorimetry curve does not change, right. It is more clear in the later one, if you see the right plot. So, the peak initial gypsum depletion peak is here, and when we add 5% of gypsum, you see it here, then beyond that we do not see any change. So, it tells you that okay, so the optimal gypsum for this cement is around 8%. Okay. Similar thing also can happen when you have mineral admixtures, right. So, here is the example. What happens when you have Portland cement, you have a CSA cement and class C fly ash and class F fly ash, right. So, depending on the chemistry, you will see very different behavior. So, you notice that this shoulder occurring only in the mix where you have class C fly ash, right. So, as we saw earlier, usually any shoulder after the main peak can be attributed to gypsum depletion. Okay. Now, if you want to verify is it because of only gypsum depletion, what you can do, you can simply add additional gypsum. That is what we saw here. So, with 5% additional gypsum, you delay this peak, and eventually at 15% we do not even see that peak. Okay. So, it was confirmed that this peak was due to the depletion of gypsum. Now, what caused that depletion. So class C fly ash basically has C3A, tricalcium aluminate. So that also competes for your gypsum. So obviously, if you compare with the class F fly ash which does not have C3A, you will see early depletion of gypsum in the mix with class C fly ash. So if we look into this ternary diagram where we put all sulfates in one corner, like in form of yeelimite and calcium sulfate, you can combine C4A3S and calcium sulfate. Here is C2S silicate phase, right, and ferrite phase C4AF. So it gives a very good idea, like where do you want to be, right? You do not want to be in this region because you do not have enough C2S, you do not have enough binding phase, right. So if you are somewhere here, that means the product you have has low durability. Also, if you are somewhere here, so very far away from C4A3S corner, that means you have very small amount of C4A3S CS, the hardening will be slow, right. So this just gives you an idea about the sweet spot you want to be in, right. If you want a normal hardening, you want to be somewhere here. If you want rapid hardening, you want to be somewhere here, right. Now coming back to the strength, right. The strength of CSA concrete, at least in this study, was comparable to Portland cement concrete, and many researchers, many studies have reported that. So here is the Portland cement concrete and 28 days compressive strength, right. When you just replace OPC with CSA, in this case the replacement was 15%, it was small increase, but I would say that you can get comparable strength to Portland cement concrete. Further, you can also look into the effect of these mineral admixtures, right. What happens when you add class F fly ash, class C fly ash and silica fume? Obviously, these are the mineral admixtures take time to hydrate, right. The pozzolanic reaction is slow. So this is 28 day strength, although it is a little bit lower, we expect it to be higher if we test it at later ages. Again, now coming back to other mechanical properties, if you look into the tensile strength, right, 0% CSA again correspond to plain OPC, and 7% CSA means 93% OPC, 7% CSA. So with that age you see increase in strength, right. So hydration is occurring and pores are being filled, right. So you see continuous increase in strength. For OPC with CSA system also, except in the system when you have 30% CSA. So what happened when you add lot of CSA, like in this case it was 30% CSA, there was a cracking because there was a lot of expansion which took place, led to this drop, right. But again the hydration is happening, right. So your cracks are being filled, and then you see again strength increase, right. Same behavior we see when we try to monitor the modulus, dynamic modulus, right. So you can see increase in dynamic modulus for all of systems except 30% CSA at early age, but then because of this continuous hydration which fills the pores, cracks, right, you see increase in strength. But in general, comparable strength, right. If you look into this 7 days, comparable strength of OPC-CSA cement paste, and here I would like to mention that this study was done on paste, not concrete. Also, it is important to look into the pore solution, right, because the pH of pore solution dictates a lot of things like corrosion, for an example. CSA cement have lower pH than OPC, but you can see that at least in this study they reported around 12.6 to 7 pH, right. I have not seen any study where it was lower than 12 basically, right. So yeah, it is lower than OPC, but not very low, right, to cause corrosion. This was the study done when CSA was replaced, right. So, you say 0% CSA is OPC, we see like 13.3 to 4, the pH in the range of 13.3 to 4 at the end of 7 days. Right. As you increase the amount of CSA, there is a reduction in pH, but even at like 30% CSA, but we see that around 13 pH, right. So, yeah, reduction in pH with increase in CSA cement, but it is not too low. If you look into the microstructure, right, we know that there is a formation of Ettringite in the crystal, and lot of formation of Ettringite, and we see that there are a lot of crystal needle-like structures, right. This was these are the micrographs, 7-day-old sample, right. So, you see a lot of needle-like structures in both. Now, it is important to look into because this is the phase which is giving you expansion, right. If you have a lot of Ettringite, you will see expansion, and we'll look into this, like we want expansion just enough to counteract shrinkage, right. So, it is important to look into factors which influence early age expansion, right. How can we quantify, right, how can we predict basically. So, we know that gypsum to yeelimite ratio is one of the factors governing early age expansion, right. When you do not have enough gypsum, you will not have expansion. Then amount of Ettringite, obvious choice, right. Degree of supersaturation with respect to Ettringite is also an important factor, okay. So, it depends, this is what is the saturation level of your sulfates, right, and these can be estimated if we know the composition of pore solution, and using thermodynamic modeling we can calculate the degree of saturation. Apart from these chemical factors, we need to also pay attention to stiffness of the cementitious matrix, right. It is like if you compare a stone versus rubber, same amount of expansion happening in rubber will cause greater expansion, right, compared to stone. So, we need to pay attention to the stiffness of the cementitious matrix. Now, if you look into early age expansion, here again we are seeing the effect of CSA addition, right. It is also important to capture this expansion very early on. Lot of conventional way of measuring expansion or shrinkage is relying on the 1-day data point, So, you cast your sample, demold it after 24 hours, right. But we know that C4A3S starts reacting immediately, and you have formation of Ettringite, and you will see expansions occurring within 24 hours. So, it is very important to capture that. For that we can use this corrugated tube, right, which allows you to take measurement immediately after casting. So, basically you fill your tube with cement slurry, and using this gauge can monitor the change in length, right. And what is important is then you can cast the parallel samples, right, the prisms which you do, and then add this data, okay. But here is an evidence that the expansion occurring within 24 hours is not insignificant, right. So, depending on your CSA content, you may have significant expansion occurring within 24 hours. Obviously, as we increase the amount of CSA cement, we see increase in expansion, right, and order of magnitude difference. 0% CSA is OPC, plain OPC. When you add 7% CSA, an order increase, 15% an order increase, right. 30% CSA samples cracked, right, because we saw that earlier in mechanical properties also there was a reduction in tensile strength and dynamic modulus, and samples cracked, okay. So, expansion within 24 hours is not insignificant, one thing to note, and there are ways to capture that. Now, we will look into the hydration of yeelimite, right, because that is what is causing the expansion, and that is what leads to the formation of Ettringite, monosulfate, and other phases. So, here again comparing the 4 different samples, OPC and sample with CSA. So, you see presence of yeelimite, right, Y. gives you peak at around 23.4 degree in XRD. And you can see that as you increase the amount of CSA, this peak is more intense, right. This is picture at 1 day, what happens at 1 day. So, you still have unreacted yeelimite after 1 day, right. But now if you look at 7 days, right, basically yeelimite is consumed, there is no yeelimite, right. So, all yeelimite has reacted and led to the formation of ettringite, right. And in addition to ettringite, you have other phases like monosulfate also, right, and hemicarbonate may form depending on the conditions. So, important thing to note is like in 7 days the hydration of yeelimite is complete. Now, depending on the use of mineral admixtures, we saw earlier in isothermal calorimetry that class C fly ash behave differently, right, because there was a gypsum depletion in class C fly ash. So, the effect of that on expansion is also is shown here basically. So, when you have class C fly ash in the system, the expansion was less compared to the plain system, but when you had class F fly ash, the expansion was increase in expansion, right. It again ties back to your isothermal calorimetry data. So, these are the techniques can be used to understand what is happening, what is the cause of this expansion behavior, right. Again here we see that within 24 hours, the expansion occurring 24 hours, within 24 hours is not insignificant. So, we all want to predict the expansion, right, depending on the phase composition. We want to know like how much a system will expand, right. So, this we have already seen when you had class C, class F, this is the plot shown in earlier slide. Now, we know that class C fly ash, again going back to isothermal calorimetry, we found that when we added the gypsum, right, that shoulder peak disappeared, right. So, that led to again this increase in expansion. When we had the 15% gypsum, right, you see increase in expansion, 20% further increase. So, this is one of the ways to mitigate this loss in expansion. Suppose your target is to achieve a level of expansion, right. Suppose you want to, so you have a class F fly ash, you want to you want your system to expand like as class F fly ash, but you have class C fly ash, then you can add gypsum basically. You know that there is going to be a gypsum depletion in class C fly ash. So, we can add gypsum and get that expansion back. And when we try to calculate this available calcium sulfate, right, we can calculate that based on the stoichiometry. We can calculate how much calcium sulfate is available for the hydration of yeelimite, right. And we saw that it was very interesting to that there was a very nice correlation basically. So, the system which expanded most, as you see, had the highest amount of calcium sulfate available for yeelimite. So, these are the simple calculation you can do to predict or compare two systems, right, because we know that yeelimite is reacting with calcium sulfate and forming ettringite, that is causing expansion. So, this availability of calcium sulfate can also give you an idea about the expansion. Now, since we are talking about expansion, it is important to look into the mechanism, right. What is that causing this expansion? What is the origin of it? So, a long time ago, Tabor did a very interesting experiment in 1916, where you had a salt in its saturated solution, right, and you put a weight on it. Then what happens when this due to evaporation, your saturated solution will become supersaturated, and that led to the growth in crystal, and that lifted the weight. The simple experiment tells us that the supersaturation gives rise to crystallization stress. Right? This test was done long time back, and we can calculate this crystallization stress. Okay. So, what does supersaturation do? Here are the two systems, the low and high supersaturation. First of all, we see that this supersaturation can be linked to the curvature, right. And we see when you have a high supersaturation, it allows crystals to grow in smaller pores. High supersaturation means higher curvature. Higher curvature means lower radii, right. So, when you have high supersaturation, that means your crystals can form in smaller pores, but when you have a low supersaturation, that will not happen. So, these two schematics depict that, right, where in high we see the pores being filled, right, smaller pores being filled. Now, this maximum crystallization stress can be calculated, right, if we know the supersaturation. This gives us the upper bound of the stress. So, if we know the composition of pore solution, right, if we know the concentration of various ionic species, we can calculate the saturation index for any phase. In this case, it was calculated for Ettringite, which is the expansion causing phase. So, you write the what is the ion activity product, because the supersaturation is ratio of ion activity product and solubility product. So, now if you know these concentrations, right, using any thermodynamic modeling software, you can calculate the ion activity, right. And basically this GEMS is the software, relies on the minimization of Gibbs free energy, can give you the saturation index of individual phase, but the input is concentration, right. And we see here now that what happens as you increase the amount of CSA, you see increase in supersaturation. So, we saw that the supersaturation gives rise to crystallization stress. So, when you have a higher fraction of CSA, you see increase in saturation index of Ettringite. People have been relating expansion to just Ettringite content, but the correlation is very weak. If you look into any problem related to sulfide attack, delayed Ettringite formation, even in this case when you have early age expansion. So, you see these are the data points, each data point is one mix, right. But same Ettringite content, if it is plotted this way, like when you normalize it by capillary porosity, you see better correlation, right. We will come back to this point why we did this, but same thing, if we know the volume fraction of Ettringite and we know the capillary porosity, the correlation improves. So, here are some factors which can influence the expansion. We saw this again, SC, I mean this volume Ettringite volume fraction in capillary pores can also be called SC, and the correlation is better, and there is a good correlation between the saturation index and expansion. Increase in saturation index leads to increase in expansion. What is interesting here, what we saw is elastic modulus, right. It is very important to pay attention to the stiffness of the matrix. If a matrix which is less stiff will expand more, right. So, as you increase the elastic modulus, you see reduction in expansion. Now, there are simple ways, obviously there are a lot of assumptions like matrix being isotropic and homogeneous, right. Elastic, we can estimate the tensile stresses, right. This is the case of cylindrical pores basically, and for the plane stress condition what we can calculate is average hydrostatic tensile stresses, right. Just to clarify this point, in cylindrical pores we are assuming these are the crystals right here causing this stresses, right. So, the sigma c is the maximum crystallization stress from thermodynamics, right. Now, based on the volume fraction of crystals, you can estimate this average hydrostatic tensile stress. And using poromechanics also, we can relate this stress to this SC factor. We saw also very like better correlation of expansion with this SC factor. We can calculate the tensile stress. So, now what happens when we try to plot. So, here is a graph compares the tensile stresses for spherical pores, cylindrical pores, poromechanics, like these are the 3 models used to predict the tensile stresses, and here is the tensile strength, right. So, basically the 30% CSA, right, you can see that we are seeing significant amount of tensile stresses, they exceed the strength, right. So, these are simplistic models, but can be useful to predict. So, all models in this case enable the prediction of failure, especially at high doses of CSA, right. That is what we also verified experimentally, right. When we measure the length change, saw cracking in the sample with 30% CSA. Now, question comes, how to design shrinkage compensating concrete, right. If you want to design concrete where you want to leverage the early age expansion due to the formation of Ettringite, how can you do that? So, there is a guide. This is a American Concrete Institute 223R, a guide for the use of shrinkage compensating concrete exists, and in that also they mention type K cement. Basically, it is a blend of OPC, yeelimite and calcium sulfate. So, right. So, how do you do it? Basically, first we anticipate the shrinkage of concrete, right, based on the experience of the local area, depending on where you are, what are the conditions, right. You know what is the member shrinkage, right. So, you know, suppose this is the shrinkage particular region, right. Now, this is the curve where you can get based on the percentage of reinforcement, right, based on the percentage of reinforcement you can calculate how much maximum restrained how much expansion you want in the maximum in the restrained concrete prism, right. So, based on this area you can calculate the maximum expansion in restrained concrete prism. And how do you do this concrete prism test? Basically, according to ASTM 878, you have this reinforcing bar, right. You pour your concrete, right, and then measure the early age expansion. So, basically in this case we are seeing the expansion from 0.04% to 0.06%, right, depending on what you have, but then again you can calculate it. If you are somewhere here and your percentage of reinforcement is here, then you would like to be here. So, you want expansion, expansion of your concrete prism, restrained concrete prism somewhere here. So, this is a guide, right, you can use. Now, we will look into the small scale versus large scale. Small scale test, when you do this concrete prism test, right, compares, you have seen similar plot before. So, this is a conventional concrete when you do not have any expansive agent, right. There is a shrinkage, the order of 600 in this case, 600 to 700 microstrain. When you add the calcium sulfoaluminate cement, you see this early age expansion and the net shrinkage is close to 0. But because of this restrain, right, because now if you look into the strain level in slab, the degree of restraint is different, is high, right. Although we see some difference, but we are not seeing like 0 net shrinkage, right. There is a difference, like OPC is here, we are able to reduce the net shrinkage. So, that is why it is important to pay attention to the degree of restraint, level of the percentage level of your reinforcement in the slab when you want to predict. Now, coming back to the application of CSA based binder, this was the field application done using OPC-CSA cement in Illinois, where 2 decks were cast side by side. You see normal deck with Portland cement, and when we replace Portland cement with CSA, right, and what was interesting to see that the deck with CSA did not crack, at early age. So, was no cracking, no sign of shrinkage cracking, right. So, it was a successful implementation of CSA concrete. This is the deck pour. The concrete was fluid workable, no issue. So, again this was a blend of OPC and CSA cement, and there was no issue in terms of pouring it in heavy reinforced areas, right. So, in summary, CSA cement can be formulated as expansive or non-expansive cement system based on user's requirement. If you want to reduce your shrinkage, then you will leverage the earliest expansion. You will okay. And successful field application of this OPC-CSA concrete demonstrates its role in enhancing both sustainability and durability, right. And the major applications of this cement include in bridge decks, concrete slabs, self-leveling floors, grouts, repair materials, pressure pipes, etc. So, where we stand now in terms of research. So, now we need to think about the manufacturing of the CSA-based cements using industrial byproducts, because that will drastically reduce the cost. Okay. Also, durability of CSA-based concrete against carbonation, corrosion and acid attack is an active area of research. As we see, the rheology is very important. How can we come up with the new chemical admixtures which can control the workability of CSA-based cement. So, these are the future possible areas of research. Thank you for your attention.